Greetings! Previously, we looked at the mathematics of interference in one dimension. Well, that's for kids. That's child's play. It's time to move on to real life and talk about interference in 2 and 3 dimensions. Really, we're talking about interference in 3 dimensions, but a lot of our pictures will be 2-dimensional. The ripple tank is the classic physics demonstration of this phenomenon called interference in 2 dimensions. We've already looked at a simulated ripple tank from the Falstad site. Here's the real thing. The MIT demos are great, but here's a demonstration from Derek of the Veritasium channel that's probably more visually effective.
I've got a demonstration here on a little pond where we can see this with water waves. I have 2 sources of ripples, which are basically like the 2 slits. When I create ripples with a single source, they travel out with circular wavefronts. Nothing particularly surprising there. But if I add a second source of ripples, then we start getting an interesting pattern. This pattern is created by the ripples from the 2 sources interacting with each other. Where they meet up peaks with peaks and troughs with troughs, the amplitude of the wave is increased. That's what we call constructive interference. But if the peak from one wave meets up with the trough from the other, then we get destructive interference, and there's
You can see that very clearly here. I guess he's just highlighted it. These are the regions that we're going to call nodal lines. Instead of nodes, which were single points on a string, for instance, with a standing wave, or a single point inside a thin column of air, now they're actually curves in space. We'll call them nodal lines. And if you were a little ducky or bug hanging out on the surface of the water, you would be relatively undisturbed along these lines. I say relatively because we're going to see that the amplitude is not necessarily 0, it's just close to 0. On the other hand, if you were a little ducky or a bug hanging out in these regions where the ripples are clearly evident, you actually would be experiencing large up and down oscillations by comparison. We call those the antinodal lines. And we'll see that the distribution of those antinodal and nodal lines or curves depends on the frequency. So when Derek here changes the frequency at which he drives the water, you'll see the pattern of those nodes and antinodes changing.
basically no wave there. And this is exactly what was happening with the light. When the light from one slit met up, peaks with peaks and troughs with troughs, they constructively interfered and produced a bright spot. But if the trough from the wave from one slit met up with the peak of the wave from the other slit, they would destructively interfere and you wouldn't see any light there. It's light canceling itself out.
He's talking, of course, about the all-important double slit experiment, which is an experiment we will look at in detail. Here's our source, presumably oscillating sinusoidally in time. So if you want to connect this with what we just looked at, think of this as the, I think it was a tennis ball being driven sinusoidally up and down in the water on the surface of that pond. Now this picture is two-dimensional, and really that example with the water was two-dimensional, but we're going to use it as a way to conceptualize spherical wave fronts. So maybe think of this as a source of sound waves, and it's an isotropic source, so you've got equal intensity in all directions, and those wave fronts are spherical and they move outwards in time. So instead of talking about motion along an x-axis, now we're talking about motion along an r-axis. And the direction of the axis is determined by the direction in which you're looking at. So really any direction you could call the r-axis. And this, excuse me, this squiggle here again is pictorial, because the squiggling here is transverse or perpendicular to the r-axis, but that may not actually be the direction of the oscillations. If you were talking about a pressure wave radiating outwards, or a longitudinal wave, then the oscillations of the air particle would be like this, back and forth, parallel, I should say, parallel to the direction of the energy travel, in which case this curve, again, is just pictorial. You may even be talking about an oscillating electromagnetic field. If this picture were representative of an electromagnetic wave, well, really the electric and magnetic fields could be oscillating in a variety of directions. So don't take this squiggle too literally. But what it is telling you is the wavelength. The peak to peak distance is the same as the distance from one wave front to the next. So wavefront is usually a word used to describe a set of points, all of which have a phase of 0 or 2 pi or 4 pi. It's like the high points on standing waves, or I should say progressive waves on a string. Or it's the regions of greatest displacement, the points of greatest displacement for a traveling longitudinal wave. So from wavefront to wavefront is one wavelength. And I'll point out now, later when we look at ray optics, we'll represent light with straight lines rather than talking about the wave nature. And the straight lines that you would draw are always perpendicular to the wave fronts. And these ripples are traveling outwards from the source at speed v, that speed being determined by, as usual, the properties of the medium. All we have to do is take our previous function for one-dimensional sinusoidal progressive waves and change one thing. Instead of talking about the x-coordinate, we talk about the r-coordinate, the distance from the origin. The relation between omega and k is the same as before. That ratio gives you the speed. There's one important change, though. We have to recognize that as the energy radiates outward from the source, it becomes more and more diffuse. In 2 dimensions, it has to be distributed around a circle of circumference 2 pi r. In 3 dimensions, all that energy would be distributed over a spherical wavefront of surface area 4 pi r squared. And as a consequence, the amplitude must decrease with distance from the source. That's just different from the one-dimensional case. In the one-dimensional case, we didn't worry about a drop-off of amplitude with distance. Now that's very important. It's an important feature of these spherical waves. And it's not difficult to show that for spherical waves, the amplitude has to drop off with the inverse of the distance. So twice as far from the source would mean 1/2 the amplitude. 10 times as far from the source, 1/10 the amplitude. So the amplitude is not a 1 over r squared law. It's the intensity that obeys the 1 over r squared law. So this is a slide from a previous presentation in which I try to convince you that the intensity should drop off with the square of the distance. If your original distance from the source was r, and you look at the amount of power that was distributed over a surface area A, that same power at distance 3r will be distributed over area 9 times A. And that means that the intensity is now 1/9 of what it was previously. So 3 times the distance implies 1/9 the intensity. That's an inverse square dependence. Put that together with the fact that the intensity for a wave depends on the square of the amplitude, as your book discusses. And here I'm using a lowercase a to talk about the amplitude from one source, because in a moment we like to talk about combining two sources and the total amplitude of the superposed wave we call capital A. Okay, so if intensity is proportional to the square of the amplitude, but it's also proportional to the inverse square of the distance, hopefully you see that means that the amplitude itself must be proportional to 1 over r. Just take 1 over r and square it, plug it in here, and you see that intensity is proportional to 1 over r squared. We're not going to use that fact too much, maybe a bit when we talk about electromagnetic waves. The main takeaway here is keep in mind that this letter A, or this amplitude A, depends on how far you are from the source. It's not constant. Okay, so here's a graphic from your book. We've got two sources, and you can tell that they're both radiating spherical waves of equal frequency. We're just going to assume that they're embedded in the same medium. The medium is what determines the speed. So the green wavefronts here are traveling outwards at the same speed as the blue waves, and we can see that the wavelength is the same. The peak-to-peak distance here is the same as the peak-to-peak distance for the blue waves. Well, if wavelength is the same and speed is the same, we know from the fundamental relation for waves that the speed must also be the same. Excuse me, the frequency. That was my point. The frequency must also be the same. So what's going on here? Let's pick one of these black dots. So this is a snapshot graph. We've frozen time, and right now we're looking at the locus of points, all of which have a phase of 0 or 2 pi or 6 pi. So this is where the water ripples have their peaks. Halfway between wavefronts is where the water ripples would have their valleys or troughs, as the caption here says. Let's go with an easy, this red dot right here. See how this red dot lies on one of the peaks from the green source? But it also lies on one of the peaks from the blue source. So you've got two peaks overlapping. That's what we call constructive interference. It's a two-dimensional analog of what we looked at previously when two progressive waves line up. Their peaks line up and their valleys line up. So this is a point of maximum constructive interference. Now, a moment later, in fact, half a period later, these peaks will be replaced by valleys because the ripples are moving outwards, right? These wavefronts are all moving outwards. So this is halfway between two wavefronts. This would be a valley that I'm outlining. Well, half a period later, that valley is going to be right here. So instead of a blue peak, it'll be a blue valley, or you could say blue trough. And instead of a green peak, it'll be a green valley or trough. So the valleys will line up at that time. And then a half period after that, the peaks will line up. So whether it's peaks lining up or valleys lining up, you still get two waves adding with the same sign, both positive, both negative. That's maximum constructive interference. So if you were that little ducky hanging out on the water, this is a point where you will be going up and down with large amplitude. Same thing for this point, right? A blue wavefront passes through it, and so does a green wavefront. Can we find one that's less obvious? Well, let's do destructive interference now. This black dot right here lies on a blue wavefront. So that's a peak as far as the blue wave is concerned, but it's halfway between this green wavefront and this green wavefront. So it's actually at a valley as far as the green source is concerned. So the valley from the green source will add with the peak from the blue source to give a number that's closer to 0. Now, it may not actually be 0, because remember, the amplitudes of those two waves depend on distance from the source. And since we're looking at slightly different distances here, they probably don't have the same absolute value, okay? So you're not going to get necessarily perfect destructive interference, but this is a point at which you will have maximum destructive interference. So you can see now all the black dots show points of maximum destructive interference. The red dots show maximum constructive interference. And isn't it interesting that they appear to lie along some sort of curve in space? And that curve is not shown yet, but we'll look at that. Important point then. One period later, the peaks become the valleys and vice versa. That does not change the fact that that particular location is a constructive or destructive interference position. Whether it's peaks and peaks adding together or valleys and valleys adding together, that's still constructive interference. And if it's a peak and a valley and then it switches to a valley and a peak, that's still destructive interference. Of course, not every point in the plane satisfies those two scenarios. You've got a point like this one right here, which is not exactly halfway between two green wave fronts, and it's not exactly halfway between two blue wave fronts either. So it's not going to be max constructive, it's not going to be max destructive, it'll be somewhere in the middle. So now I've got some extra subscripts to talk about the displacement from source 1 and the displacement from source 2. Look at this, I didn't even update the subscripts. Let me fix that. Okay, that's better. This is the displacement at this particular point in space. So we're looking at the total displacement right here. We've got a contribution due to the wave from source 1. So the distance from source 1 to the point in question I will call R1. And the corresponding distance to source 2 is called R2. This is the progressive wave that it's just reached this point from source 2, and this is the progressive wave that has just reached at time t the point in question. And remember, A1, A2, they don't have to be the same. In fact, they almost certainly will not be the same if the two distances are different. So how do we go about adding these two up? Well, before we talk about that, if the sources are identical, meaning they have the same inherent phase constant, if these two phase constants are equal, then they're oscillating in sync in time. The two waves that arrive here may still be out of phase due to a path length difference, but there's no inherent phase difference. So the example with Derek oscillating the tennis balls in the pond, it looked like they were being driven in sync. So for that example, the inherent phase difference would have been 0. But depending on where you're looking at the total wave, there would be a phase difference because of the path length difference. Now, if you think back to the math for the one-dimensional case, we used a whole bunch of trigonometry, but the outcome depended in part on the fact that the individual waves had the same amplitude. That's what allowed us to factor out the A. And in this example, it's not going to be so convenient. This was the result. This is for the one-dimensional case. That's why we're seeing the coordinate x instead of r. This quantity in here in brackets is what we call the total or overall phase difference. Remember, it had a contribution from the path length difference, but there was also the inherent phase difference. I've highlighted in blue here the part that tells us that the net wave is also a progressive wave, and everything else out front was the amplitude. Oops. So this is the overall amplitude. It's this entire quantity out front. We'll call that capital A. And it's easy to see that the amplitude is greatest when the cosine takes on the value 1. We know that cosine goes from 1 to negative 1. Actually, it doesn't matter if the cosine takes on the value 1 or negative 1, right? If this quantity were equal to negative 1, then its absolute value is the same as 1. So the conditions for max constructive interference, well, that's when you have the largest possible total amplitude. So cosine has to take on its greatest absolute value. In other words, the cosine needs to be 1 or negative 1. Max destructive interference would be when the cosine takes on its least possible value. In this case, 0. That's only possible because for the one-dimensional case with equal amplitudes, you don't have to worry about the fact that the amplitude changes with distance. So it's possible for those two waves to cancel totally or perfectly. Well, happily, even though your book doesn't show how to add two different progressive waves with different amplitudes, and truthfully, I'm not sure I've ever seen that done. If I have seen it, I've forgotten it. The end result is the same, or part of the end result. This is the part that ends up being the same. So there may not be a nice expression like this that we can develop, but this fact remains true. Wherever you are on the surface of the pond, the locations of max constructive interference, where the peaks and the peaks or the valleys and the valleys overlap, that's where the cosine function takes on the value 1 or negative 1, and where the peaks line up with the valleys of the other source, I should say the peaks of one source line up with the valleys of the other source, this must be true. So that's why it was worth memorizing this, that the total amplitude is proportional to the cosine of the overall phase shift, or phase difference, I should say, divided by 2. Let me repeat that in words. When you have two sources interfering, even in 2 or 3 dimensions, even if they have separate amplitudes, provided that they have the same frequency and they're in the same medium, the total amplitude at any point in space is proportional to the cosine of 1/2 of the overall phase difference. That's a nice result to remember because it allows you to do a lot of calculations. There's a lot of problems you can solve with that one result. Well, this is equivalent to this condition, right? You can get this formula from this because when does cosine take on the value 1 or negative 1? The argument inside would have to be pi or negative pi or 3 pi or negative 3 pi. If you write that down in symbols, you end up with this formula. When does cosine take on the value 0? Well, the argument of the cosine would need to be pi over 2 or 3 pi over 2 or 5 pi over 2, or just take the negative of all those. That's where these formulas came from. You've seen these already. I presented them in the last presentation, even though we were talking about interference in one dimension, and I said that you can just think of delta R and delta X as being the same. Let's look at an example of a point where there's maximum constructive interference. So this would be one point on an antinodal line. Let's start with point A. You can see that point A, by looking at the blue wavefronts, you can count that it's 2 wavelengths from source 2. And by looking at the green circles, you can count 1, 2, 3 wavelengths from source 1. So it's 3 wavelengths away from one source, 2 wavelengths away from another source. The difference between those distances, and I've called those distances R1 and R2. The distance is 3 lambda minus 2 lambda, or in other words, 1 lambda. And that's what they're pointing out here. Delta R sub A means the path length difference for the waves arriving at A. One wave comes from this source, one wave comes from this source. Okay, so that's equivalent to looking at the picture and recognizing that a green wavefront and a blue wavefront overlap there. Let me emphasize this again. The points on this drawing where a blue circle and a green circle intersect are not the only points of maximum constructive interference. Those are the easiest to recognize. It would be nice if we could do another one. Yeah, I think you can see right here. If I leave the dot here, do you see how that dot is halfway between 2 blue circles? And it's also halfway between 2 green circles. So it's a valley for the green circles, and it's also a valley for the blue circles. That's also a point of maximum constructive interference. Half a period later, blue and green circles will be intersecting right here. So that's another sort of easy type of point to find in this picture. But that's also not those two situations, blue and green circles intersecting, or a point between 2 green circles and 2 blue circles, those aren't the only possibilities. That's why it might be better to look at an actual simulation, which we'll do in a moment. What about destructive interference? Just one. We'll do this real quick. This dot right here is right on a green circle, but it's in between 2 blue circles. So it's at a peak for the green wave, but it's at a valley for the blue wave. The peak and the valley will sum to a number close to 0. That's max destructive interference. The other way to think about it is you can count them 1, 2, 3 wavelengths from source 1, but it's only half plus 1 plus 1. That's 2.5 wavelengths from source 2. So if you look at the path length difference, 3 lambda minus 2.5 lambda is half a wavelength. The difference between the two paths is half a wavelength. That's the condition for destructive interference. And that's actually not something I've emphasized enough yet. Yeah, so I've got a slide for that later, but let me point this out now. These are supposed to be identical sources. We're supposed to assume here that they're being driven in phase. That means synchronized in time. So this quantity, delta phi sub 0, it's gone. It's just 0. And then you could get rid of the 2 pi, get rid of the 2 pi, solve for delta r, the path length difference, and you would find that the path length difference has to be an odd number of half wavelengths. That means half a wavelength, or 3/2 a wavelengths, or 2.5 wavelengths, etc. What you find if you try to locate all the points at which you get max constructive interference. So let's take one class. Look at all the points where the path length difference is a full wavelength. And you find that they lie along a hyperbola. You may have recognized this shape or this curve. And there's a nice word from math. We call it the locus. The locus of all points for which the path length difference is equal to 1 wavelength is a hyperbola. Now this line is what you would call a degenerate hyperbola. It's the only degenerate case here. So the red curves are showing the loci of points for which you get max constructive interference. Those would be the antinodal lines. Red curves, antinodal lines. And along this black curve, for instance, the path length difference is half a wavelength. That's the condition for maximum destructive interference. So that would be a nodal line. Again, this is only true if we're talking about identical sources. If the inherent phase difference is 0, then this is what the pattern of nodal and antinodal lines looks like. Here we are in the ripple tank. I'll walk you through a number of the features. The first thing you might want to do is increase the resolution to the extent that your computer hardware allows. If you've got not much RAM, you might have to keep the resolution low. I think I can do a little better than this. Actually, before I do that, let's observe that with low resolution, the nodal curves are barely discernible. You can see these fuzzy curves along which the ripples are not as easily seen. Those are supposed to be the nodal lines. And where the ripples are easy to see, those are the antinodal lines. Let's see how much easier they are to make out after I increase the resolution. Did it make a huge difference? A little bit. Okay, now my computer is slowing down, so I'm going to back up just a bit. Is it just me, or did that make us zoom a little bit? Okay, increasing the brightness really does help. Now it's very clear where the nodal curves are. You can also experiment with a different color scheme. Kind of psychedelic, isn't it? Okay, so it's worth tinkering with these options. These nodal curves, which look an awful lot like hyperbola or hyperbole, I think that's plural, those are the loci of points for which you get max destructive interference. And what is kind of missing from this visualization is the antinodal lines, because it just looks bright everywhere in here between nodal curves. But the actual antinodal line we've already seen is that vertical one, at least here. And then in between each pair of adjacent nodal curves would be another antinodal curve. So let me see if I can find a color scheme that shows that a little more clearly. Yeah, not really. So I guess this simulation is best for visualizing the nodal curves. 3D view. I'm almost afraid to see what happens here. Whoa. I never knew it had this. That is so cool. Okay, so that helps you see the antinodal curves because you can see where the curve or the surface is highest. Now, this term 3D is a little misleading because it's not actually showing you interference in 3 dimensions. It's just a 3-dimensional representation of 2D interference. The height of this surface here shows you the amplitude of interference in 2 dimensions. So it's not a truly 3-dimensional graph. This is just too cool. I wish I could take credit for this. What else can we mess with? What happens if we change the frequency? And this will be a major topic in the next chapter or a couple chapters from now. Watch the spacing of the nodal curves and how it changes with source frequency. I turned the frequency way up, and those nodal curves got much closer together. If I put the frequency near 0, we should see them spread out. Big time. So the directions of destructive interference clearly depend on the source frequency. And later in the semester, we'll be able to calculate that. We're going to look at a generalization of this type of interference to 3 dimensions, and we'll use a very simple approximation that allows us to just use one trig function, really. That's coming up. This might be a good time to point out that this simulation makes it look like we've got 2 sources like the tennis balls bouncing up and down in water, but you get the same effect even if you're talking about shining light through 2 slits, the famous double slit experiment. So presumably you've got a source of light above this barrier here. Maybe it's a very wide laser beam, and then the beam can only pass through these 2 slits. And the 2 slits now act as if they're independent. Well, I shouldn't say independent, but they're 2 new sources of light. And you can see you get the same phenomenon. We're still looking at nodal lines with antinodal lines between them. The picture's rotated, but it's essentially the same phenomenon. So the slits are acting just like 2 sources. So 2 slits or 2 sources like tennis balls bouncing up and down in a pond, same interference phenomenon. Let's go back to the actual 2 sources and check out one more feature. Ooh, I don't like that one. That offends my eyeballs. Even worse. Look away, look away. Okay. What happens if I change the phase, the inherent phase difference? Right now they're oscillating together, and that's easy to see because if I stop it, check it out. We've got a blue wave currently emanating from the bottom source. Same thing for the top source. How about this? Let's think of the blue sections as peaks and the light blue sections or cyan as valleys. So you've got a peak coming out of both surfaces or both sources at this moment in time. But I can right click on one of the sources, go to edit, and add what they're calling a phase offset. And they'd like the phase offset in degrees. So if I want these to be out of phase by pi radians in time, that would be 180 degrees in time. And now when I pause, you can see that a peak is currently coming out of the bottom source while a valley is coming out of the top source. So they're now 180 degrees out of phase, or you could say pi radians out of phase in time. The inherent phase difference is now pi radians. Now, since I just switched it, that update in the information is just starting to travel outward. So you can still see the original location of the nodal curves, but look, now there's a new location. This direction is going to propagate all the way outwards after I hit play again. But I think you can see that the antinodal and the nodal curves have switched directions, which is really easy to understand because that additional shift of pi in time, the inherent phase difference, it just reverses the roles of points of constructive or max constructive and points of max destructive interference. So let's check that these new nodal line directions will extend all the way outwards. Yeah, in fact, I think what I'm going to do is do it both ways, take screenshots, and then we'll compare. Here's a good set of parameters for visualization. I've got the 3D setting checked. Don't put the brightness up too high because then it makes the amplitude awkward. Pick a color scheme that you like, and then you can even zoom in. This is probably the best visualization I've seen. It's very clear the direction of the antinodal lines versus the nodal lines. As promised, here's a screenshot of the interference pattern for, let's see, it looks like we've got the two sources out of phase in time. There's an inherent phase shift of 180 because you've got a valley, that's the cyan color, just now being emitted from the top source and a peak being emitted from the bottom source. Check out the directions of the nodal curves. Here I just switched to two in-phase sources, in-phase in time, and the directions of the curves are different. So let me go back and forth a couple times there. Definitely different. And for good measure, I threw in a screenshot of a 90-degree phase difference. Okay, somewhere in the middle. And now let me briefly try to convince you that those loci of points of constructive, max constructive, or max destructive interference are indeed hyperbole. Here's a coordinate system. Let's overlay an X and Y coordinate system onto our, the surface of our pond. So we're representing three-dimensional interference with the two-dimensional picture. And I'm going to use the letter lowercase d for the distance between the sources. That is a letter that we'll use later in the semester, and it's kind of a standard choice of letter to represent the distance or separation between the sources. Source 1 will be the top one. And I'll let you think about this if you'd like to confirm this. You don't necessarily need to know this for, I take that back. There is an example in your chapter that uses Pythagorean theorem to describe the distance from field point. That's when I say field point, that means the point, some arbitrary point at which we'd like to know the total amplitude of the displacement. You can use Pythagorean theorem to find the distance from this point and source 1. So this point would have coordinates x and y. X and y are the coordinates of this arbitrary point. And of course, if we look at a different point, the coordinates will change. Now, what are the coordinates of this source? Wouldn't they be 0, d over 2? The x coordinate of this point is 0, but its y coordinate is positive d over 2. The coordinates of source 2 are 0, negative d over 2. So this is really just an application of the distance formula that you should have learned in analytic geometry. So what ends up happening if you use these expressions for R1 and R2, and then you apply this condition? Delta R would be this expression for R2 minus this expression for R1. The condition for maximum constructive interference is that, and I just blew past an important point, or did I? Here it is, right here. Okay. I really should have emphasized this more earlier. I said this a moment ago. These formulas become a little simpler if you're talking about identical sources. Two sources which are being driven in phase in time, so no inherent phase difference. Then you can get rid of delta phi sub 0. The 2 pi's cancel from both sides, and you end up with these simple conditions. If the two sources are in phase in time, then the condition for constructive interference is just that the path length difference be an integer multiple of wavelengths. That's it, very simple. If you want maximum destructive interference, the path length difference has to be a half integer multiple of wavelength. So either half a wavelength or 3/2 of a wavelength or 5/2 of a wavelength, etc. Most of the problems we're looking at involve identical sources. So you probably are going to use this condition more than you'll use this one. Okay, so if we assume identical sources, then we would set the path length difference equal to an integer multiple of the wavelength. That's the condition for max constructive interference, and that gives me this equation. Now, what does this graph like? We know the answer. You know the answer. You've seen it in the pictures already. I'm not going to do all the algebra. I did work it out on paper and convince myself that these are indeed hyperbole. How would you go about doing that? Well, I'll skip the details, but I ended up arriving at an equation that looked like this. And it's just a hop, skip, and a jump to turn this into this. See how there's a negative sign in front of the x squared? I think what we would do here is divide the whole equation by a times c, or is it? No, d. Yeah, you want to turn this d into a 1. Before you do that, though, you'd have to complete the square. So complete the square here, and then that's going to change the constant over here. Whatever that constant is, you divide the whole thing by that constant to turn the constant into 1. And you can see you would have a minus sign in front of x squared. So this is what you could call a vertical hyperbola. If the minus sign was in front of the y squared instead of the x squared, you'd flop this hyperbola over by 90 degrees. But it makes sense that we wind up with this because that's exactly what we were expecting. Okay, so the nodal curves and antinodal curves are in fact hyperbola. And the last thing we can add here, and this is definitely the cool part, we're using a two-dimensional picture to represent what's actually happening in 3 dimensions. So when you think about a source here and a source here, the argument that we made to locate the nodal lines or the antinodal lines, it doesn't have to be specific to this particular plane. Pick any plane that passes through those 2 sources. For instance, imagine a plane that's cutting perpendicular to the screen. So, a sheet of paper coming out of the screen such that it passes through both sources. The same argument would be valid in that plane. So you could rotate these hyperboles so that they lie in that plane. In other words, just revolve these hyperbola about an axis through the 2 sources, and you're talking about a hyperboloid of revolution. That's really what the nodal and antinodal surfaces would look like in 3 dimensions. And your book doesn't present that. I've seen other textbooks where they address this, but it's kind of fun to remember that for 2 sources, which actually radiate isotropically in 3-dimensional space, you're talking about nodal and antinodal hyperboloids, surfaces of maximum destructive or maximum constructive interference. And I think it's fairly clear why we're not going to find a simulation of that. How do you visualize that? It's difficult to use a 2-dimensional space like the screen of this computer to represent a function that really depends on 3 coordinates. But this graphic does a pretty good job. All right, so there's a fun fact to impress your friends at parties. Parties, what are those? That was before COVID. The surfaces of maximum constructive or destructive interference are, in fact, hyperboloids.